Hello guys, welcome in this video. In this video we are going to talk about the gas vortex confinement node, and this node is made by side effects in Houdini DOP networks in order to break the diffusion and the uniform shapes in the simulations like smoke simulations, or what I usually call the mushroom shapes. Okay, and this node actually creates and amplifies vortices in your simulation. So a vortex means rotation like this, or it happens in the ocean vortex means that the ocean is going to rotate. Okay, so it adds vortices to your simulation, which makes your simulation more dynamic and improves its locking a lot. Okay, so to do this, or this node, what this node does to your simulation is that it computes your, or okay, let's talk about the math behind this node and let's see how it's built inside Houdini. The first thing that happens is that it computes the curl of the velocity field, and I talked about the velocity before. I talked about the curl before. When you have your velocity, for example, rotating like this, if your velocity is rotating like this, your curl is going to be the axis of rotation. Okay, so it's rotating around this axis, and the more rotation you have, the higher the length or the magnitude of this curl, and you can revise the curl video if you want. Okay, so you compute the curl of your velocity as the first step, and the second step is that you compute the magnitude of this curl. So you compute the length of the curl, so you'll have higher curl magnitudes in the areas that have more vortices and more rotation. Okay, as I said, the curl determines the rotation and the degree of the rotation and the axis of the rotation. So when you compute the magnitude of the curl, you will have higher magnitudes in the more rotating areas of your simulation. Then after this, you'll compute the gradient of this curl magnitude. We can call it curl mag. Okay, so now after you define the magnitude or compute the magnitude, you'll have areas with higher magnitude of curl. As I said, the higher rotation areas, or the areas where the simulation rotates and is more dynamic. Okay, and you'll compute the gradient of this, and this means that you will have a new field, okay, where the vectors will look in the direction of the highest rotation. Okay, so if your curl magnitude means the amount of rotation, then the gradient of this means that you'll have vectors looking at areas with highest amount of rotation. As we said, the gradient is a direction of the steepest ascent. Okay, so now we computed the curl, we had the axis and the amount of rotation. We computed the magnitude of the curl, which means the amount of rotation. Then we computed the gradient of this amount of rotation. So now we have the direction of the steepest ascent, or the direction where the rotation increases mostly, which is our gradient. Then what we will do after this is something called cross product. Let me change the color. Something called cross product. Okay, so what is the cross product? The cross product simply means if you have two vectors in 3D space, like these two vectors, the cross product here, so if this is vector A and this is vector B, the cross product between these two vectors will result a vector that is perpendicular to both of these vectors. So it will look like this. Let's change the color more. It will look like this. So this is A cross B. Okay, and if we change it to B cross A instead of A cross B, the resulting vector will be perpendicular to both of them, but in the opposite direction. So this is B cross A. Okay, so this is just the cross product. We find a vector that is perpendicular to both vectors, and it's not an interchangeable. So this means that A cross B is not the same as B cross A. Okay, not like the dot product. Okay, we'll talk about the dot product, and it's interchangeable, but this one here will result a vector that is perpendicular to both of them. So what we can do now is that we can take the cross product between this gradient of the curl magnitude. Okay, we'll take the cross product of this one here and our curl vectors, or the axis of the rotation, and the result is going to be a vector that is perpendicular to both of them. So this new vector, this new cross vector, if we add it to the velocity, it will introduce more rotation and more vortices into our simulation, and we're going to show this inside Houdini. Okay, let me show this. I tried my best, creating an example here, just for showing. It's not an example, in the course or something in DOP networks. It's just a SOP example. Okay, so for example, if we create a velocity field, we have just this box here, and we have points from volume, and if we create a field like this where you have a big vortex, maybe I can just make this something like 0.05 maybe. Okay, so here you have your velocity is like a vortex. Maybe I can show this here. If your velocity is like this, okay, something like a vortex like this. So now if you compute the curl of this, it will give you the axis of the rotation. So here you have rotation happening, you have your rotation happening in this direction, anti-clockwise direction. Okay, maybe we can put this to 0.15 or something, or maybe 0.1, yeah, something like this. Okay, and you see here that the amount of rotation is higher outside. It's more wide, so it's higher at the outside. So if we compute the curl of this, you'll have the axis of the rotation here, and it's calculated here, as you can see. If we now change this, yeah, so this is your axis of rotation. So it's looking upward here, as you see, it's looking upward. So this is the axis of your rotation, and this is the curl. And as you can see, it's more yellow at the outside, meaning that the magnitude of the curl is highest at the outside, as the degree or the amount of rotation here was higher at the outside. Okay, we had our vectors here more white, which means that the magnitude of them is higher at the outside, so they are going to rotate your simulation higher at the outside. So here the curl gave us the axis of the rotation, which is here to the up direction here, and it's giving us the amount of rotation here. You have the higher amount of rotation at the outside. Okay, but I'm not going to show this example because it's not going to be clear if we show the next steps with this example. I will show another example where I just created simple velocity field, and we will talk more about creating fields in the next chapters and the custom forces and all of this stuff, but this is just for demonstration. Just imagine that this is a velocity field that we are going to use in our simulation, that we are going if we just apply something like this to our simulation, it will make the smoke, for example, it will make the smoke go in a vortex rotation like this. Okay, and here I feel like this is just looking upwards, but you know, it's not very uniform. It will make the smoke go upwards, but in a slightly random, you know, a slightly random matter here, so it's not going to be that uniform. Okay, so let me visualize this. If this was our velocity field, let me increase the trail length. Yeah, we can increase the trail length to 1.5, for example. If this is our velocity field, it's making our smoke it makes our smoke move upwards, but not very uniform. Okay, so if we compute the curl of this, you'll have now the axis of rotation and the amount of rotation. You see here you have the axis of rotation in the different areas. Okay, and the yellow areas have more rotation, so they have more magnitude of the curl. Okay, so you have the axis, and the more yellowish areas here means that you have more rotation happening in this area, and the length or the magnitude of the curl is higher in this area. Okay, so what we are going to do now is that we are going to compute the curl magnitude, and I'm not explaining what happens inside the sops, I'm just showing you just for demonstration, and we will build, you know, nodes like this maybe in the next chapters. Okay, or you can build another example like this in the next chapters. So after we computed our curl, we can compute our magnitude of the curl, then the gradient of this magnitude, and if we show now the gradient here, it is going to be something like this. Okay, so we here have the vectors looking at the areas with highest rotation. So if you visualize this here, for example, this area here, you'll have your vectors looking at the areas of highest rotation. Okay, and maybe we can make this 0.8 or something. So yeah, something like this. So you know, this is not something useful for our simulation. You know, some of you now say that why do we do something like this? It's not something very useful. But if you now normalize this gradient, okay, normalize it, we can normalize it before the cross product. Okay, so here before this cross product, we can normalize this, which means dividing the gradient of the curl magnitude by its length to create or to get a unit vector looking at the same direction. And we talked about normalization before. Okay, so if we normalize it, and take the cross product between it and the curl, as we said, you'll have something like this. And you now see that it creates a new field. If you add to your velocity, you will have more vortices. So if you see now, it's adding a vortex here, it's adding a vortex here, here. So this is a very great way to add vortices to your simulations. Okay, you can use this, and this is the idea behind the gas vortex confinement. You know, I know it's not looking very intuitive when you see the gradient, when you see the curl, but it is surprisingly amazing when you calculate the cross product and you have now your vortex direction. And if you add something like this to the velocity, it will add a lot of vortices and a more dynamic look to your simulation. And this is an example just for demonstration. I didn't go through the nodes, but what we are doing is just something that we are going to do in DOP networks. Okay, we are going to calculate the curl and the gradient, the curl magnitude and the gradient of the curl magnitude and the cross product, and all of this we are going to do it in DOPs, but I just demonstrated it in sops so it becomes very clear to you. So now let's apply this, all of that we had here inside Houdini. We have here our simple Houdini sourcing setup that we used in the gas turbulence and in the gas threading. Just sourcing from a sphere. Okay. I don't know why everything is okay, our simple setup here, the source of the sphere, or the sourcing from a sphere. So we are going to create 3 fields using the gas match field. The first field is going to be our curl field, and it is going to match our velocity because the curl is a vector field. So we are going to match our velocity field. So now this is a gas match field, create velocity, and we can create another gas match field and create a scalar field, and the scalar field is going to be called the curl magnitude, and the magnitude surely is a scalar field, and it's going to match the density. Okay, so here create curl magnitude, then we are going to create the last field that we want here, and we are going to call it vortex direction. So it is a vector field, vortex there, and it's going to match our velocity, and it's a vector field. Now we are going to merge the 3 fields here. Okay, and we are going to connect this to our velocity update. So now we have 3 fields ready for our calculations. So let's add another merge node. Then the first thing that we are going to do is we are going to calculate the curl of the velocity field. So this is done using a gas analysis, the node that we use a lot. The source field that we are going to operate on is our velocity, and we are going to calculate its curl. Then we are going to store this in the curl field. So gas analysis, calculate curl. Okay, So now we calculated our curl, and then we are going to add another gas analysis. Okay, and it is going to be called calculate curl magnitude, and we are going to calculate the length of our curve and store it in the curve magnitude. Okay, the same process. Then we are going to create another gas analysis node. Delete this. And in this gas analysis, now we are going to calculate the gradient of the curve magnitude as we said. So here calculate curve gradient. Okay, and we are going to the curve magnitude gradient. Okay, so we are going to calculate the gradient of our curve magnitude and store it in the field vortex direction. And now the next step here, so here we calculated the curl and the magnitude and the gradient. Then we are going to normalize this curl gradient or this curl magnitude gradient. Then we are going to do a cross product between the normalized gradient and the curl. Okay, so here we can add another gas, I'm sorry, not a gas analysis, a gas cross. Okay, which does a cross product between two fields. Oops, no. Sorry, we are going to add another gas analysis. Okay. And in this gas analysis, we are going to call it normalize our vortex direction. So we are going to operate on our vortex direction. We are going to normalize it, but we are going to store it in the vortex direction also. Okay, so we are just editing the field. We are normalizing it and storing it in the same field. We don't want to create so many fields without any usefulness. So after this, we can do the gas cross node, which takes two source fields and does the cross product and store it in the destination field. So here we are going to cross product between our vortex direction and our curl field, and we are going to store this or store the result in the vortex direction. So now we are still storing in the vortex direction after we do the operations. So cross vortex direction and curl, and finally after this we will add this to the velocity as a force.